Electromagnetic induction is when we actually go and use the cutting into a magnetic field to create current. So as you can see, when we have electromagnetic induction, we are going to induce current, which means that there is no power source that's going to be connected to it. So when we induce current here, we're actually saying that there is no current, but because there's a change in the magnetic field, it will cause current. So if you have a solenoid, and now I'm going to draw it three-dimensionally, a solenoid soft core that's wrapped with a coil of conducting wire. If I actually take a bar magnet, and now remember there's no power source connected to this conducting wire, so I can use a galvanometer or a voltmeter to go and measure if there's actually voltage being created. A galvanometer has the same basic function here. It just shows us, is there actually potential difference being created? So I connect my galvanometer to my conducting wire, and then when I take my bar magnet and I insert it into the solenoid, this being my north pole and this being my south pole, as it goes in, there's a north pole that's induced on this side of the solenoid. And now if you take your thumb and you point your thumb in the direction of the north pole, meaning that your thumb will point towards it, your fingers will point in the direction in which current will be induced, which is going to be anti-clockwise, as you can see. Now, if a north pole is created, north and north will repel each other. So as the magnet now moves out of the solenoid, instead of a north pole being created, a south pole is going to be created here. Which means if we now go and we point using our right hand in the direction of the north pole, if you point in the direction of the north pole, you will see using your right hand that the current now is going to be clockwise. This is the basics of Lenz's law as well, and you need to be able to just identify the direction of induced current around the solenoid for your exams. Lenz's law is no longer part of the exam guidelines, so you do not need to have a definition. You will see in your workbook that they ask you in your mind map for Lenz's law. We don't need that. All we need to know here is that we can still use our right hand rule to figure out the direction of current, and we can use our thumb to identify the north pole for us. Then also, if we have a look at magnetic field strength, we said that magnetic field strength is identified by the symbol B, and the unit is Tesla. Magnetic flux, this is the symbol for magnetic flux. It's measured in Weber. Now, magnetic flux, it almost looks like a circle, like a magnetic field, and something cutting into it, that symbol. That's what it reminds me of. If we go and look at the formula for magnetic flux, it's the magnetic field strength times the area, and then this cos theta is basically the angle between the magnetic field and the normal on the surface of an object that cuts into that magnetic field. So when we use BA cos theta, if we have an object and this is our magnetic field, for example, I'll indicate direction, and the object cuts perpendicularly into this magnetic field, we know if we go and we draw the normal on it, that the normal will be in the same direction or parallel to the magnetic field lines, and therefore this will give us an angle of 0 degrees. Cos 0 gives us 1. We can then also go and use this information to go and calculate something we call the change in magnetic flux. Change in magnetic flux is the same as every other change in something formula that you've seen in physical science. It's going to be the final magnetic flux minus the initial magnetic flux. Sometimes what can happen is the angle can change. An object can move out of a magnetic field. We know when it moves out of a magnetic field, this angle becomes 0, because if it moves out of a magnetic field, the normal is at a 90-degree angle. Cos 90 will give me 0. So that's one thing that can change in terms of magnetic flux. Another thing that can change in terms of magnetic flux is the magnetic field strength. So there are two ways in which there can be a change in magnetic flux. Now we're going to go and combine all of this in something that we call Faraday's law. So Faraday's law basically says that we can go and create EMF. So if you go to a store and you go and buy a cell or a battery, you'll normally see that there's a positive terminal and a negative terminal, and then it indicates an amount of volts that that cell or battery can then deliver. That value is called the EMF, and this is the symbol for EMF. We measure it in volts, just as we measure potential difference in the same unit here. There's a formula that we need to know here. We know that the EMF is going to be equal to the amount of windings, and it has a negative sign here in front of the letter N, N standing for the amount of windings in the solenoid, and the negative sign basically is there to indicate that the induced EMF across your conductor causes a current and a magnetic field that opposes the change in magnetic flux. You are not going to be asked to explain that negative sign. You need to just accept that this formula includes this negative sign. So it's going to be equal to the amount of windings multiplied by the change in the rate of the magnetic flux. So change in magnetic flux over time. And we write it like this: change in magnetic flux over the change in time. This formula then we can use to calculate the EMF. So for example, if we have an object with 300 windings, we will substitute 300 into N's place. The change in magnetic flux will be a value in Weber, and then remember change in time in seconds. When we substitute these values, our final answer will be in voltage. Sometimes they will tell you that the change in magnetic flux per time, and then they'll give you a value. That just basically means that they are giving you Weber per second. So just be aware of that. It can happen sometimes. The most important thing about Faraday's law is that it's something that we use again in grade 12. And that's why it's important for you to be able to interpret it, to do calculations and problem solving using it.